Okay, so we are in Module 1, Lesson 1, and I am going to show you kind of how the lesson design works for this. So what I would do is I would actually open a couple documents. I would open your assignments so that you have that open. This will make a copy for you, so I'm going to open it so that I have it here. So I can kind of cross-reference as I go through my work. Today, it looks like all you have is to take notes. So you're going to take a picture of your notes and examples that you do from the PowerPoint. Okay, so that's the first thing I always do is I open it up. I'm going to see what's expected of me, whereas on Thursday, you guys are going to actually be working on some problems as well. So this gives you an idea of where you're going. So today, we're just going to take notes, probably on a piece of paper. When you come in class, or if you come in class, I know some of you guys are distance learning, you'll kind of have to create your own. But when you come in class, I will be giving you guys an engineering notebook to take notes in. Okay, so from here, I'm now going to go into the lesson for the day. So I'm going to get back into the course. I'm going to go to Module 1, and I am on Lesson 1. And you guys are obviously here because you are watching the video that I'm recording right here. But this is the lesson for today. You are going to go to the PowerPoint, and you're going to take notes on slides 1 to 23. Okay, you'll notice I have a wheelbarrow example here. This is going to come into play when we talk about levers and different class levers. We have a class 1, class 2, class 3 level, the lever that we're going to be talking about. And this is helpful in seeing different places where it's seen in the real world. I love that diagram because it is difficult to tell the difference between those without having the notes for them. Okay, so let's go ahead and get in here. I know you guys are able to look at this PowerPoint and go through it on your own, so I'm just gonna highlight a few things. I'm not going to go over every single part of this PowerPoint because you can go back and take notes on it later. It's there for you. But here, we are gonna be talking about 6 simple machines over the course of the next 2 weeks. After that, you guys will move on to a different topic, but we're going to talk today specifically about a lever, and then tomorrow you'll get into wheel and axle and pulley, and then next week we get into the, next week on Monday it's lesson 5, you get into the inclined plane, wedge, and screw. Okay, so you'll get into those. The first thing you need to know is this idea of mechanical advantage. Mechanical advantage, definitely something you want to write down. And it is the ratio of the distance traveled by effort and the resistance force. You try to create a mechanical advantage in most machines. Machines want to have some kind of mechanical advantage. If you're thinking about, let's say, lifting something, okay, if you're lifting something, you want your machine to put in as little effort as possible because otherwise the parts wear and such. Okay, so you want it to put in as little effort as possible to raise whatever it is that you're trying to lift. So most of the machines that we create have a mechanical advantage of some kind. Okay. Okay, so we'll talk about that ratio now. Like for example here, if I'm lifting this box right here and I'm just lifting it straight up, that's gonna take more effort than it will if I slide it up this wedge right here, okay? Or we call this an inclined plane. If I slide this up that inclined plane, it's actually gonna take a lot less effort than if I'm just lifting it straight up. So that's the idea of a mechanical advantage. It basically takes the same thing. You can see this distance is a lot shorter than this distance traveled. So the distance traveled in this one is going to be 4 times greater. See, it says here. So this has a mechanical advantage. This one right here, this box that's sliding up the inclined plane, it has a mechanical advantage of 4 to 1. Notice how that's a number bigger than 1, that's 4, but it's a 4 to 1. And what that tells us is that the effort force magnitude is 4 times less than the resistance force. Okay, so I've just decreased it by that much. Okay, so think about a maybe like a refrigerator. Okay, this box is a refrigerator. If I had to lift a refrigerator straight up, I actually couldn't do that, right? But if I take it and I push it up an inclined plane to get it to snap into whatever place it's going to be, that's probably manageable for me to maybe be able to do. So it creates this 4 times the distance, but it's 4 times less force. That's the idea of mechanical advantage. So we will also be talking about work. work. Work is going to be the force that you apply times the distance parallel to that force. Okay, so the work is force, and that's definitely something you want to write down. So we have mechanical advantage and we have work. So work is going to be the force times the distance that's parallel to the force that you're putting on. So here's the force. You can see you're going to do the parallel distance here to the force. Okay. So work is the product of the effort time. The distance traveled will be the same regardless of the system of mechanical advantage. So I'm going to kind of get into that here. So mechanical advantage, our mechanical advantage is, and we're going to have two different concepts with mechanical advantage. We're going to have what's called an ideal mechanical advantage and an actual mechanical advantage, and we will have equations for those like we did for work in just a minute. But the idea of a mechanical advantage, if it's greater than one, then you have proportionally less effort force is required to overcome the resistance. So that's where we had in the last example, it was a 4 to 1. That's larger than 1. Our mechanical advantage is 4. That means that it's less effort to actually push the force. If you have a mechanical advantage less than 1, that's the opposite. You have proportionally greater effort force is required to overcome the resistance. So now you have to put in more force. Where do we see things like that? Well, we see them in the gym. Those, the weights that we have, those are designed specifically to have a greater force that you need to put in. So that would be a mechanical advantage less than 1. That's when you want the force to actually weigh more, right? Most of the time our machines are designed so that way we have a mechanical advantage greater than 1. So just kind of know that going into it. So here are your two different formulas that you definitely need to write down. So we have an ideal mechanical advantage. It's called IMA. And I remember this because in a minute I'm going to tell you AMA, which is actual mechanical advantage. And we'll talk about what that means in a minute as well. But IMA is DE, the distance of your effort force, over the distance of your resistance force. And I'll show you in a diagram what that means in a second. But it's the distance of your effort force over the distance of your resistance force. You can see those down here. Okay, we are doing this, it's a theory-based calculation. So we're talking a frictionless environment, which we know is not actually true. When I'm sliding that thing up the inclined plane, there's friction that's happening there, and we're not taking that into consideration with the IMA, the ideal mechanical advantage. We're not taking into consideration friction. So just be aware of that. The way that I remember this equation is it's IMA DE dr. That's how I remember it's DE over dr. It's I'm a deer. Okay, I'm a deer, DE over dr. That's how I remember it. You're going to hear me say it even in class. When we do our calculations, I'm a deer. I'm a deer. And then the next one is going to be the opposite. So I want you guys to see that now we're talking about forces. We're talking about forces. It's going to be very obvious whether you are calculating ideal mechanical advantage or actual mechanical advantage. The actual mechanical advantage, the difference is you're talking about friction is now involved in it. So we always calculate an ideal, like a frictionless environment, but then we also have to calculate our actual mechanical advantage because we need to take into consideration friction. Like that's something that's real in real life. So in this one, we're talking about the forces. And you'll notice that it's FR, the resistance force, over the effort force. That is opposite. It's the resistance over effort. This one is effort over resistance. So they're opposite of each other, and that's where the confusion can happen. So that's why I remember I'm a deer for the first one. I'm a deer, DE over DR. And this one I remember as AMA free. I know that's kind of weird because that's not really a thing, but AMA free, FR over FE. These are opposite. Okay, it's going to be fairly obvious in our problems when we get to them, whether you are going to be calculating actual mechanical advantage or ideal mechanical advantage. The problems will just say, calculate the mechanical advantage. They won't say actual or ideal. mechanical advantage. So the way that you're going to know that is within the problem. If they're giving you the forces of your effort and your resistance, then you know that you're going to be calculating actual mechanical advantage. If they're giving you distances traveled instead, then you know that you're going to be using ideal mechanical advantage. Okay. When these two things are equal, we're going to talk about that. We will be setting these two equal if you're given all of them to figure out how close your ideal and mechanical and your actual mechanical advantages are to one another. Okay, so here are a couple different problems. This one's going to have, these are windmills. You maybe see these if you've been out to Palm Springs before, or Palm Desert. This right here would obviously have a mechanical advantage greater than 1. There are many, many things that would have mechanical advantages greater than 1. That's usually why you build machines. But here you're turning, you're spinning these fans, the fan blades, and it's taking little effort, but it's creating a lot of force moving down, and that's what causes the energy. In the gym, this would be a mechanical advantage less than 1. So when you're thinking about a gym, those are obviously meant to purposely give you weight. If it's purposely making your effort bigger, then that's going to be a mechanical advantage greater than 1. Okay, the last thing we're going to talk about are levers for now. So when we talk about a lever, there's going to be 3 different kinds of levers that can happen. So I'm actually going to grab just a pen to kind of talk about them. We're going to have level 1, level 2, and level 3 levers. That's why I put that other diagram on the notes. But I first want to talk about where the fulcrum is located. So you'll notice in that top one, the fulcrum is right here. This is like a teeter-totter, right? This is like a teeter-totter. That's that concept. Okay, so we have that can happen. That's where forces would actually be acting down on both of them. So that's what you're seeing in here. You're seeing forces acting down on both of them. Okay, this one is very common as well. If you think about this right here, the blue, I guess that's like a dark blue, that dark blue arrow is going to be your resistance force. So that's what you're seeing on both of these, resistance, effort. So on the seesaw, if this is your resistance, to counteract it, you're going to put weight here as your effort force. This one, if your load is in the middle, okay, or your force, or your resistance force is in the middle, think of this almost like a wheelbarrow. You'd be lifting it up. This is your effort force, this green arrow, okay? The fulcrum is right here. Imagine on a wheelbarrow, that would be a tire. That would be a tire. So this is like the concept of a wheelbarrow. This one right here is interesting. If you look, the resistance force is up. The resistance force is up. And the effort force, I'm sorry, the resistance force is not up. The resistance force here is down on the end, and therefore you're lifting from the middle. Your effort force is in the middle and you're lifting up. We're gonna have an example here. This is like a tweezer. The idea of a tweezer, which by the way has a mechanical advantage, less than 1, because you're putting a little tiny force on it and you want it to pull something out, okay, to get a splinter, let's say. So that's actually going to have also a mechanical advantage less than 1. Okay, here's the idea of a first-class lever. A first-class lever is going to be that teeter-totter example. You have your resistance acting down here, so to counteract that, you have to put your effort on the other side. You'll notice that the idea of a fulcrum, so if the fulcrum was right in the middle, if you put 5 pounds on this side, all you would need is 5 pounds on the other side. It's a mechanical advantage of 1. It has a mechanical advantage of 1. And that's because it's going to take the same amount of effort and resistance if the fulcrum is right in the middle. If the fulcrum is closer to the effort, okay, so now you have your resistance here and the fulcrum is closer to you instead of the effort that you have to put on it, you're going to have a mechanical advantage less than 1. It's going to take a lot of effort. Like if I put 20 pounds here, it's going to take a ton of effort if the fulcrum is close to me. That's going to take a lot more effort for me to push down. That's not ideal usually. So in the other, you'll see this one, to get a mechanical advantage greater than 1, instead what you would do is you would actually have the load here and you would put the fulcrum closer to the load. Then you would have more room to be able to push down, and that creates a mechanical advantage greater than 1. We see this actually in teeter-totters downtown at the water park. There's 2 seats on either side. So my daughter weighs more. So because she weighs more, and then my son weighs less, right? So the fulcrum happens to be in the middle there, but if I put my daughter and son in the same spot on those teeter-totters, then my daughter would be like this because my daughter weighs more. But they've done this idea of a mechanical advantage. My son, I needed him to have a mechanical advantage greater than 1. So what I did is I actually put my son further out on here to give him a mechanical advantage. Okay, I put him in the further seat and I put my daughter in the closer seat. Then they could actually teeter-totter back and forth. I have a video of this. If you come into class, I'll likely pull up that video so that you can actually see it in action. I put him in the same spot and it's like this. Boom, my daughter's done. Okay, so there's no teeter-tottering. But then I move her in so that my son has a mechanical advantage, and then they just can do this back and forth. So it's very interesting to see this in action. I created a mechanical advantage for him by putting him further out to give him more leverage. Okay. The second class lever looks like this. It's the wheelbarrow, the classic wheelbarrow. This is why we have wheelbarrows, because it creates a mechanical advantage. You'll see right here, always has a mechanical advantage greater than 1. The fulcrum is at the very end. Your resistance is in the middle, somewhere in the middle, and the effort is up. So the force is down, the effort is up. That's opposite of the lever 1. When you have that situation, then you always have a mechanical advantage greater than 1. Okay, next one is a third class lever. Oops, skip right over it. The fulcrum is located at the end, kind of like a wheelbarrow, but the forces are different. So you'll notice that the resistance force is on the end here. And so now your effort force is in the middle, like pulling up on it here, or think of it like a tweezer, right? You're pushing down here. Okay, you're pushing down here. Your fulcrum is at the front of it, and you're pushing here. And it's pulling against you. It's pulling against you. That's how tweezers work, right? They always have a mechanical advantage less than 1. There's always a mechanical advantage less than 1. Okay, I'm going to keep going. So the last couple slides here, a moment. We will be calculating a moment as well. So you will want to write this down. A moment is the distance times the force. And what a moment is going to do is it's going to be talking about that like idea of rotation. Okay, so it's going to talk about that ideal of rotation. So like if you're thinking of this right here, the image that's given to you, and you have your forces and they're not equal and they're not counteracting each other, I should say, that's probably better. It's going to send it into motion. It's going to send it into motion. We're going to be trying to, this entire unit, stop that motion and figure out how do we balance these forces. So this is the idea of torque or a moment. Okay, so here is the lever moment calculations that you guys will start to do on Thursday. So in here, if we have this is an example, we have 15 pounds being exerted here, and it is 5.5 inches away from the fulcrum. So if we want to know what is the effort on this one, what is the effort on here, then you would have the 5.5, the distance, times the force being exerted, the 15 pounds. That's only giving you half the story though. We need to also go in and talk about the resistance. And again, this is the idea of static equilibrium. We don't want to, static equilibrium means we're trying to balance these weights so that we're not spinning in motion. We don't have this rotational equilibrium if it's unbalanced. Okay, so in here, the last thing that we'll kind of talk about is this idea where if we have this side, in order to make it equal, we're going to have to set these two equal to each other, these two sides. So if I want to know, well, I have 36.23 pounds that goes here. How far is this right here? I can actually solve for any of these, but we're going to set each side equal to each other. So we're going to have that idea of a moment. The effort moment has to be equal to the resistance moment. So here we have that 15 pounds times my 5.5. That's going to have to be equal to my 36.2 times my distance for the resistance, which we don't know yet. Then we can just go in and mathematically solve that. We can solve that. So that's what's going on there. Okay, so last concept, I'm actually going to skip this one for now. We'll talk, you guys can take notes on this if you would like to. It's the idea of the ideal mechanical advantage is dE over dR. And in this one, you'll notice that the 2 pi's actually go away. It's just going to be the effort times the resistance arm, but we'll get into that more a little bit later. This is another example of that. I will talk about the actual mechanical advantage. So in this one, it's really just setting up the different ratios on top of each other. So if we're doing the AMA, the actual mechanical advantage, we're doing the FR, AMA free. FR, the resistance force. So here's your resistance force, 32 over your effort force. It looks like we have an AMA in this one of 2 to 1. 2 to 1 is the actual mechanical advantage. The ideal mechanical advantage is something that we actually did in this one. If you guys looked, it's the distance effort over the distance of resistance, which ended up being our 5.5 distance over our 2.25. We had an IMA of 2.44 to 1. Why is your IMA larger than your AMA? The concept there is for you guys to understand that your ideal mechanical advantage is probably going to be larger because friction is not involved. Your actual mechanical advantage is going to be a little bit lower. Sure, we create these wonderful machines that have really high IMAs, but in reality, we know that friction, gravity, there's different situations that are making it where our actual mechanical advantage is not quite as high as our ideal mechanical advantage. The last thing you guys have here to take notes on is that if I ask you, well, what is the percent efficiency of your machine? All you're doing is taking your AMA, your actual mechanical advantage, and you're dividing by your IMA, your ideal mechanical advantage. Then you're going to multiply by 100 to just make it a percent instead. So when we do that, we have 2.0 over my 2.4, and we get that this machine is 82% efficient. No machine in real life will ever be 100% efficient. That's not a thing. We unfortunately in real life have gravity, we have friction. Those things will make it so that we'll never have a machine that will work in a frictionless environment. Okay, so those are the notes for today. Hopefully that will make sense. We'll actually do some practice problems starting tomorrow. We're taking notes again, and then the next day we start doing some of these problems, the AMA, the IMA type problems with the levers. Okay, that is all.